define something known as the product of two groups, and there is a result which says that the product itself is a subgroup if and only if Hk is equal to Kh. Okay, if you recall from group theory, this was the necessary and sufficient condition for the product Hk to be again a subgroup of G. Now, in place of U and V, we have in place of uv we have u plus v, because our operation now is addition, and u plus v is equal to v plus u. Why? Because addition is commutative. And in fact, in group theory also we mentioned this fact that in an abelian group, any two subgroups H and K give rise to a subgroup Hk. So that's what we have here. Just from that itself we can conclude that u plus v is a subgroup of R under addition. Sometimes it helps to link whatever you already know to the things that you are doing right now. Right. So after this we have the sixth one. Now this is sum of two ideals. Just like that, we also have product of two ideals. If u comma v are ideals of R, let uv denote the set of all finite sums of elements that can be, they are writing it in a somewhat different manner. Let me write it in my way. UV denote the set of all finite sums of elements of the form UV, where U belongs to U and V belongs to V. Now we have to prove that UV is an ideal of R. Okay. Note that unlike the previous exercise, here we are not considering UV to be the set of all elements of the form UV. That's not the thing. It is something more. It's actually not a collection of elements that look like this, but collection of elements that can be generated from elements that look like this. We start the solution and it will all become clear. Okay, so what should a typical element in UV look like? Let U1, U2, UN belong to U. Should I write like this or in a slightly different? Okay. I need to take more elements. Let AN, then C1, C2, etc. Cn belong to U. and B1, B2, this is M, Bn, comma D1, D2, etc. D, M belong to V. Okay. So an arbitrary element in this set UV looks like this: A1, B1 plus A2, B2 that is finite sums. This is the finite sum of elements of the form this, where the first element is coming from U and the second element is coming from V. Note that this n it can be any positive integer. In particular, this is also an element of UV. However, n can be quite large. Here n is 1, n can be 100, 1000 or any higher value. So now you can probably realize why I have taken these elements. I am going to take two arbitrary elements in UV. Okay. Then one element in UV is of course what I have already written just now: A2, B2 plus AN, BN. And the other one is C1, D1 Actually, I should not have taken the thing, started off the solution like this. The proper way to write is this: let this and this be two elements in UV where you have to write these things. But you get my point, what I am trying to say here. Now we are trying to show that this difference again belongs to UV, so that UV will become an additive subgroup of R. Okay. Now recall the elementary calculations in a ring. We can write this in this way: A1, B1 plus A2, B2 plus etc. AN, BN plus minus C1, D1 plus minus C2, D2 Now this in its entirety, this is again a finite sum of elements of this form, where the first element is coming from U and the second element is coming from V. Y belongs to UV since minus C1 minus C2, these are again elements in U. And what property we have used here, you can probably understand. Minus C1 D1 is equal to minus C1 D1. It's that thing. Also, minus of this is equal to, that is additive inverse of this is equal to the sum of the additive inverses. And that is coming from this group theoretic property. If you have two group elements, G1 and G2, you take their inverse, you get G2 inverse, G1 inverse of course, but here we can take G1 inverse, G2 inverse also, because we are dealing with additive group which is abelian. Okay. So that means thus UV is a subgroup of R under addition. Next we have to verify the other condition for an ideal. Next, for any R belonging to R, we have this. R times A1 B1 plus A2 B2 AN Bn, okay, and this is equal to, first we can apply the distributive law. Distributive law means its extended version. And then we can use the fact that multiplication is associative, thus writing these products like this. This belongs to UV because A1, A2, A3 up to AN, these are all in U. And since U is an ideal, these multiples also belong to U. And like that, the other product. Note that you have to verify both the things, that is, a ring element times an ideal element belongs to the ideal, also the ideal element times the ring element, because it's not given to us that the ring is commutative. That's not always the case. So we have to verify both the things. In fact, in one exercise just before this one or the one before that, we have seen that AR is not necessarily an ideal. So where from one side the multiplication does not take us inside the ideal. So we have to be careful to calculate both the things. Belongs to UV. Okay, we can write the reasons here in bracket. Since RA1, RA2, these things belong to U, and P1R, P2R, these things belong to V. Okay, hence UV is an ideal of R. Note that for ideals also we have defined in a way, at least the symbols suggest so, addition and multiplication. These things will become important when we study commutative algebra and algebraic geometry. There, ideals are very important. In fact, they are almost central. Okay, so we will see those things sometime in future. So after this, we have a small exercise which is about this one. In exercise 6, prove that this ideal UV is actually contained in the intersection of U and V. It's not difficult at all.